Hello everyone and welcome back to this course. So last class we were discussing about this formation enthalpies mean and how they can be evaluated, how they can be quantified, calculated if we have a very general reaction involving species A and B getting converted into M and N. So we can find out the enthalpy of the reaction if we know the formation enthalpies of products and reactants. So we can subtract these two as we can see here. And if this comes negative, which means the enthalpy of the reaction is negative, that underlines that it is an exothermic reaction and heat will be released through this reaction. Whereas if the enthalpy of this reaction is positive term, which means it is an endothermic reaction and it will require the energy to basically proceed. So, in order to, we went ahead and we also sort of found out the relation between enthalpy and its dependence on the temperature, and when we saw that the formation enthalpy of this reaction at any arbitrary temperature which is different from standard temperature and pressure conditions depends on its reference formation enthalpy and a factor that involves the heat capacity. So, it is basically integration of Cp which is dependent on temperature from T0 to T. And the same also is slightly available, rather connected to entropy term. So, we have to have the reference entropy term plus the integration of Cp over T with respect to the temperatures T0 to T. So, moving on. So, we have seen this both enthalpies and entropies are dependent on formation enthalpies, and as we can, let me write this up, that for solids, so for solids the Cp term is merely constant, it does not depend much on the temperature. So, temperature dependence is almost 0, I would say, or almost negligible, because as we increase the temperature, the energy content in those spaces increase, whereas this phenomena does not happen much in case of solids and liquids, and that is why the heat capacity almost remains the same. However, in case of gases, gaseous species or gases, the Cp is function of temperature, which we will see as and when we proceed, and that is why we need to take into account its integration over the temperature, and then we can only find out the enthalpies and the entropies. So, it becomes very important for those reactions that involve gaseous species, because then we have to consider this Cp as a function of temperature and then we can proceed. So, that is how we will move ahead, and then let us move on to another concept, relationship between Gibbs free energy and the electrical work. So, it is a very simple derivation. Let us get started. So, we all know G is Gibbs free energy is basically H minus Ts. So, let us also input for enthalpy, which is U plus PV, and this is again minus Ts. So, this is again still the Gibbs free energy. Let us differentiate these things in order to understand how Gibbs free energy depends on what parameters. So, dG equals du plus Pdv plus V dP minus T ds minus S dt. So, let us call this as equation 1. So, what we know from first law of thermodynamics was from first law of thermodynamics, we have dq equals T ds, which is also equal to du plus dw. So, this dw, that is work, let us make this very generalized form of work. So, we can write this is du plus dw electrical work plus dw mechanical work, So and then we can also go on adding different other types of works. So basically we are focused on electrical work. So as we will proceed, we will get to know that. So this du equals, sorry, I go back and then I can say this is dq equals, so this is dq equals, or this is also equal to T ds. Let me change it for calculate for internal energy. So we have T ds minus P dV minus dW electrical, because in our case the mechanical work is 0, because in case if you take an example of fuel cell or electrolyzers, there are no moving parts. So mechanical work is 0 there. So we are only focused on the electrical work. So let's call this as equation 2, and then from equation 1 and 2, let's substitute for Gibbs free energy change, and then we have T ds minus P dV minus dW electrical plus P dV plus V dP minus T ds minus S dt. So if you look at this TDS plus TDS and minus TDS goes, then we have VdV and minus PdV go, and so what we are left with is basically V dP minus S dt minus dW electrical. Let's call this as equation 3. So in case of, let me write this, in case of fuel cell or electrolyzers as well, or electrolyzers, so the temperatures and pressure are normally held constant. So for example, if I show it here, so this is, let's say, a fuel cell, like a black box you can say, and if you connect a thermocouple here, the temperature will be almost constant, and since it works typically at 60 to 65 degrees Celsius, which are, in other words, the temperature is constant. So we can say change in pressure or change in temperature is 0, and that is what leads us to very important relation, that change in Gibbs free energy of any reaction is given as an output in terms of the electrical work. So basically electrical work output is, or input is, basically nothing but reference to the change in the Gibbs free energy. So let me write T and pressure are held constant here. So then only we can write this expression, or rather only then this change in Gibbs free energy is equal to dW electrical, it's valid. So let's move on and let's quickly find out the relation between, so relation between this electrical work and the potential. So we have done half work, we have related Gibbs free energy and the electrical work. Now let's move ahead and connect the electrical work with respect to its potential. It's very again simple demonstration. So we know electrical work is nothing but electrical potential into charge. Okay, let me write this up. This is the charge in coulombs, and this is nothing but the electrical potential, in volt. And what does charge in coulomb mean? So Q equals nothing but N times F. So what is this NF? What is F? F is Faraday's constant, which is nothing but roughly 96,485 coulombs per mole. And what is N? N is the number of moles of electron, okay, involved in that particular reaction. So the product of number of moles of electrons and the Faraday's constant gives how much charge is basically being transferred during that reaction. So let's go ahead. So we have electrical work equals N F into E, and if we now rearrange what we know from previous expression, work electrical is nothing but minus of delta G reaction equals, this is an intrinsic quantity. So as we can see, this is on the smaller font, not the capital letters. So NF E. So let's rewrite and or rearrange this term and say that electrical potential is nothing but minus of delta G reaction divided by NF. That becomes a very important term, very important expression, that if we know the Gibbs free energy of any reaction, we can convert this into the electrical potential. We can get to know what is the electrical potential of that particular reaction. So that's how we will proceed. Let's take a very simple example. Our conventional hydrogen and oxygen fuel cell. Okay. What is the reaction? H2 plus half O2, that gives 1 mole of water. So 1 mole of hydrogen reacts with half mole of oxygen, and that gives 1 mole of water. Let's find out enthalpy, or let's have this one first case. This is the first case. What is our second case? Let's increase the concentration. So we have 2 moles of hydrogen plus 1 mole of oxygen, that gives 2 moles of water. Okay, this is our case 2. So what is our enthalpy, Gibbs free energy of this reaction? Delta G equals minus 237 kilojoules per 1 mole of hydrogen, or I can say on a intrinsic quantity, this can be on per mole basis. So this is for complete reaction. I can write the same expression as delta G equals delta G naught at STP, it is minus 237 kilojoules per mole. Okay. So let's find out how we can find out the potential for this reaction. Number of moles of electrons involved in this first case are 2. So let's go ahead and find out the E naught. So we are going, E naught means this standard or the reversible cell potential, because we are calculating the potential at standard temperature and pressure conditions. That is why it is E naught. So what we know, it is from the last slide, we know it is delta G naught divided by NF, or it can also be written as delta small g naught by NF. So this is minus will remain same. Delta G naught is minus 237. It is kilojoules. So let's convert that into joules. This is joules, and N is 2. What is Faraday's constant? It is 96,485. This is, let me write, this is in coulombs per mole. And if we calculate this, this comes somewhere close to 1.228 volt, and or this is close to 1.23 volt. So reversible cell potential of hydrogen oxygen reaction, no matter how we do it, whether we do it electrochemical way or we do it through normal combustion reaction, the enthalpy will remain the same. And if you are just converting into potential, it comes somewhere close to 1.23 volt. Let's take the second case, wherein the number of moles of reactants are increased or rather doubled. So in this case, your enthalpy, Gibbs free energy is also increased. It is twice the what we had earlier, 237 kilojoules should be delta G, and number of moles of electrons in this case are not 2, now they have been doubled because the reactants have been also been doubled. So this is N is 4. So let's again take the same expression, E naught equals minus delta G naught by NF. So what is our Gibbs free energy? It is minus of twice 237,000 joules divided by 4 multiplied by 96,485. So, as you can see, this again remains the same, this is 2, this becomes 2. So, we ultimately get to the same expression, same substitution. So, this also comes close to 1.23 volt. What does it imply? It implies that even if we change the concentration, the reversible cell potential does not change. What changes is its free energy. The Gibbs free energy changes, it gets increased or decreased accordingly with respect to concentration, but the cell potential, reversible cell potential at STP remains same. So, let me go ahead and write that up. So, electrical potential remains unchanged despite the changes in concentration of species. So, what it implies is if the concentration of species or other reactant species, that is hydrogen or oxygen or any other fuel and oxidant, if that changes, it ultimately changes the Gibbs free energy. However, reversible cell potential, that is E naught, remains unchanged. Very important conclusion. So, no matter how you change the concentration of the species, you increase its concentration, decrease the concentration, the Gibbs free will change, but what does not change is its output, what you see at the terminals of the cell, the E naught remains unchanged. Let us move on. Let us find another example. So, we have now changed the fuel, we have taken methanol plus O2, that gives CO2 plus H2O. This is in the liquid form. So, let us balance this reaction up. So, we have 3/2 and then we have CO2 will remain same and then we have 2 H2O. So, what are its enthalpies and the entropies? So, we have for methanol, then we have O2 and then we have CO2 and then we have water in liquid form. So, what is your enthalpies of formation? Delta HF naught, this is in kilojoules per mole, and then we have entropy, standard entropy in kilojoules per mole per Kelvin. So, we have this is minus 238.5, entropy is 127.19. The formation enthalpy of oxygen will be 0 because it is a pure material. So, it has been existing in the environment in its original form. So, hence the enthalpy of formation for O2 is 0. So, we have entropy at 205, CO2 is minus 393.51 and entropy is 213.79. For water, the enthalpy as we know it is 285.83 or 286 also we can write, and this is 69.95. Okay. So, now we have the all formation enthalpies of the reactant and product species. We also have the entropies at STP for different species. Let us go ahead and find out the enthalpy of the reaction at STP. So, we know we need to subtract the formation enthalpies of products, reactants from the product. So, let us first write this expression. So, it is products, for products it is CO2 And what is the formation enthalpy of CO2? It is minus 393. And what is molarity? The concentration is 1 mole. So 1 into minus 393.51, right? So this is the formation enthalpy of the CO2. It is 1 mole. What is the product? What is the water molarity? It is 2 times minus 285.83. So that completes the formation enthalpies for the products minus now we need to subtract the formation enthalpies of the reactants. So it is CH3OH is 1 mole. So it is 1 times minus 238.5 and plus 3 by 2 times 0. Since all the quantities are in kilojoules per mole, the enthalpy of the reaction will also come in kilojoules per mole. So if we calculate this up, it comes somewhere close to minus 726.67 kilojoules per mole. Okay, so this is enthalpy of the reaction. Let's go ahead and find out the enthalpy of the entropy of the reaction as well. Second one step. So delta S reaction is, again we will take the same concept. We need to subtract the reactants from the products, the entropies of reactants from the products. So we go ahead 1 into minus of 213.79 plus twice the 69.95 minus 3 by 2 times 205 plus 1 times 127.19. So if we calculate this, this comes somewhere close to minus 81 joules per mole per Kelvin. Reaction. So once we know the enthalpies and entropies of the reaction, we can find out the Gibbs free energy, and we can again calculate the standard reversible potential, which we will do a little later. Let's slightly focus our attention on this quantity NF. What is this quantity NF? It's basically, as we know, this E naught is equal to G naught by NF. So this NF is like a bridge. It's like a bridge, or it's a connecting term between two very important terms, that is energy and potential. So if we know the energy, we can find out the potential, or if we know the potential, we can find out the energy, if provided we know the number of moles of electrons involved in that reaction. So it's like a bridge. We can play around these terms, and we can find out the other if the one quantity is known. And let me just underline this term one more time. NF is basically, F is your Faraday's constant, which is nothing but 96,485 coulombs per mole, and N is the number of moles of electrons involved in that particular reaction. So if we know these two parameters, or either one parameter, that is number of moles of electrons, we can find out NF, and if we know the enthalpy, if we know the Gibbs free energy, we can find out the reversible cell potential. So let's move on. So let's quickly have a look at what is this Faraday's constant and how that number, magic number 96,485 has been derived. It's basically Avogadro's number multiplied by the Q. Now what is this Q and what is this Na? This is the meaning of Avogadro's number, number of electrons in 1 mole of any species. So, this is the number of electrons in 1 mole of any species, that is your Avogadro's number, and this is equal to 6.22 into 10 to the power 23 electrons per mole. So, if I have any species, any 1 mole of species, it will contain roughly 6 into 10 to the power 23 electrons in that 1 mole. And what is this Q? Q is the charge per electron. So, it is charge per electron, and how much is that? This is 1.6 into 10 to the power minus 19 coulomb per electron. Okay. So, let us find out what is your Faraday's constant. It is basically product of these two numbers. So, I am not going to substitute it. I will just write this like this, and then this, if we multiply these two, we get this magic number 96,485 coulombs per mole. So, it is the Faraday's constant that makes this electrochemistry very interesting, and that is why we can see a huge current flowing in the circuits once we deploy fuel cells, or if we deploy electrolyzers or batteries or capacitors. It is only the Faraday's constant because of which this entire magic has brought into the picture. So, it is very important, and we also need to understand this number of electrons that are involved in any reaction. Let me take H2 half O2 plus, that gives H2O. So, number of moles of electrons that are involved in this reaction are 2. So, likewise we need to find out the number of moles of electrons involved in any reaction, and that ultimately leads to calculation of reversible cell potential or the Gibbs free energy if the one term is known. So, let us move ahead and write another, or let us go to the next point, determination of reversible potential with change in temperature In other words, what happens if we deviate from standard temperature pressure conditions? So, in this case your T operating temperature T is not equal to T naught. So, let us find out. So, in this case, once the change is brought into picture, so whenever we have the cell operating differently or rather at different temperature and pressure conditions, the reversible cell potential is no more 1.23, it deviates, and it is different from what we have observed earlier. So, that is the change that we are going to see. So, let us start with the derivation. So, we know this G equals H minus Ts, it is a very standard expression, and then we again substitute for enthalpy, which is U plus PV minus Ts. So, let us differentiate, try to understand what parameters this Gibbs free energy depends on. So, dG equals du plus Pdv plus V dP minus d ds minus s dt. Okay. So, from first law of thermodynamics, this is nothing but dq, right, and this is also nothing but the heat transferred according to the first law of thermodynamics. So, let me write it here as per first law of thermodynamics. So, in other words, this dq cancels the another dq. So, this can be taken out from the reaction equation, and we can write dg equals V dP minus S dt, right. So, we are trying to observe the change in Gibbs free energy with respect to temperature or change in the temperature. So, we need to write dG with respect to change in temperature, keeping pressure constant, that gives us equal to minus of S. Let us move ahead. So, let me write that equation one more time. So, dG by dt, keeping pressure constant, it is minus S. So, this change that we are observing is at very at a very differential change. It's a very differential change. What happens when the system goes from state 1 to state 2? The change is delta. So, we want to observe the change when the system undergoes a complete transformation from state 1 to state 2. What is the change in the Gibbs free energy with respect to temperature? So, that is nothing but d delta, and I am going to bring it or trying to make it intrinsic. So, delta G reaction with respect to delta change in temperature, we am still keeping pressure constant. This will be minus small s now, because everything is molar basis. So, what is your delta G? We know this earlier. What is, so this is d by dt of delta G is minus n f e. If you recall the previous derivations, keeping pressure constant, this is minus s. So, minus becomes plus, and this n and f, they are constant for any given reaction. So, they cannot be differentiated. So, they will be taken out, and we will divide the right hand side with nf. So, that gives us the expression dE by dt as plus s divided by n f. And now we want to see the change in this cell potential, reversible cell potential. So, what is dE? dE is nothing but L dot Et minus E naught. So, this is the change that we are observing. So, we are writing in place of dE, and dt is nothing but the arbitrary change from the reference temperature T naught, which is still equal to as, I forgot to write delta S here. This is delta S because for the complete reaction it is delta S. So, it is plus delta S by n f. So, let us rearrange the terms, try to find out what is our Et and what does it depend on. So, Et equals, or Et minus E naught equals delta S by nf multiplied by T minus T naught. And if I now write it for Et, which is equal to E naught plus and change in the entropy divided by nf minus T minus T naught. So, this is the expression that defines the changes in the cell potential for any arbitrary temperature T, provided we know the change in the entropy and we know the temperature at which the cells are operated. For example, if I am having a fuel cell which is operating at, let us say, 60 degrees Celsius, now that 60 degrees is different from that of your standard temperature pressure condition. So, in that case your E naught will no more be existing, it will be Et. So, Et has to be found out by knowing these terms such as E naught and entropy change, and the other terms we can find out the Et. So, the question arises, can this Et be larger than E naught, or it can be smaller than E naught as well? So, that depends primarily on the terms on right hand side. As we can see, the terms, that is, first one is your entropy change. So, if this entropy change is positive, then this E naught plus will become plus, I mean it will be getting added to the E naught, and that is how we can say that Et will be larger than E naught. If this entropy change is negative, it is less than 0, then the term on right hand side, that is, it will be E naught minus the second term will arise, and that will decrease the cell potential with respect to reversible cell potential. So, this is what we will be looking at, and if it is 0, then there will be no change in the cell potential with respect to reversible cell potential. So, I am going to write 3 cases. So, if this delta S is positive, your Et will be greater than E naught. If this entropy change is negative, Et will be less than E naught, and if it is 0, Et will be equal to E naught. There will not be any change in these terms at all. So, let us take the first case, on what factors this entropy change depends on. So, let us take the first case, entropy change is positive. Okay. What does it mean? It means the entropy of the system or that reaction has increased. So, that happens only when you have, or by and large it happens when the number of moles of gaseous products is greater than the number of moles of gaseous reactants. Gaseous reactants. What does it mean? Let us take an example of, say, carbon oxidation. So, C plus O2, that gives carbon monoxide. It is a partial oxidation. So, let us balance this reaction up. So, it is 2C plus O2, that gives 2CO. Okay. So, in this case, if you look at the number of gaseous reactants and products, the carbon is solid here. So, we have 1 mole of oxygen gas as a reactant, and that 1 mole of gaseous reactant is ultimately getting converted into 2 moles of carbon monoxide. So, here the gaseous products are more compared to that of reactants, and therefore, in this case the entropy of the reaction is likely to increase. So, this will, if we perform this reaction, the entropy change will be positive. Let us take the second example wherein the entropy change is negative. So, the same case will be applicable. Number of moles of gaseous products will be less than that of the number of moles of gaseous reactants. The example is our very conventional hydrogen oxidation, H2 plus 4,2, that gives H2O. This is in liquid form, this is solid. So, if you look at this reaction, we have 1 mole of hydrogen gas, we have half mole of oxygen gas. So, together it is 1.5 mole of gaseous reactants getting converted into no gaseous product if this happens at low temperature. So, in other words, you have number of gaseous products are less than that of the reaction. So, in this case the entropy change will be negative. There will be less chaos in the system if this reaction takes place. So, that is why the entropy change is negative, and that is why, in as per this illustration, your entropy change will be negative, and that will ultimately lead to our second case wherein the ET will be less than the E naught. What is your third case? Third case is there is no change in the entropy. So, in this case, number of moles of gaseous products are equal to that of the reactants. So, example, so this is an example. So, example is complete combustion of carbon that ultimately gives to CO2. So, here if you see, 1 mole of oxygen is getting converted into 1 mole of carbon dioxide. So, number of gaseous products, number of moles of gaseous products are equal to or is equal to number of moles of gaseous reactants. So, in this case there will be no entropy change, and in this case if we calculate the enthalpy and the ultimately reversible cell potential at arbitrary temperature T, it will be equal to that of its reversible cell temperature. So, we write this up again. So, ET is equal to E naught plus delta S by NF T minus T naught. So, as this entropy change is positive, ET will increase. That is what we discussed, and if there is entropy change negative in our case. So, for H2O2 reaction, this entropy change is negative. So, ET will decrease. However, so I can say it, so ET will be less than 1.23 volt. This is your reversible cell potential E naught. So, what does it mean? Does it mean that we should always operate the cell at STP all the time to get the maximum reversible cell potential? That is not the case. If you look at the practical applications of these fuel cells or electrolyzers, they are conventionally operated at very elevated temperatures, typically 60 degrees or 70 degrees in case of low temperature fuel cells or electrolyzers, 150 to 200 degrees Celsius or 600 degrees Celsius or even 1000 degrees Celsius. So, they are way higher compared to standard temperature and pressure conditions, and one of the reasons for that is we have higher catalytic activity observed when we have the elevated temperatures or elevated operating temperatures, and that is one of the reasons why we get good performance if the cell temperature is increased. So, thermodynamically, yes, we can say that there will be drop in the cell potential. However, kinetically we get a larger advantage, and that is the reasons why these cells are typically operated at higher temperature and pressure conditions. So, let me write this up. So, as temperature increases, the kinetics, which we are going to get into the kinetics of the reactions. Kinetics of the reaction increases, and therefore, the performance of the cell, whether it is a fuel cell or electrolyzer, any thermochemical, any electrochemical system will increase. The cell also increases. So, this is one of the reasons why the cells are operated beyond STP. So, operating temperature and pressure are different than that of the STP. So, this is the reason for that. So, with that we come to an expression of understanding the temperature dependence or effect of temperature on the reversible cell potential. In the next class, we will study the effect of change in pressure on its reversible cell potential. With that, I close this session. Thank you, everyone.